In this video, we'll discuss the causes of rotational acceleration and really just restate Newton's second law. So we've seen for rotational quantities, we replace a delta x with a delta theta. We replace a velocity with a angular velocity. We replace a linear acceleration with an angular acceleration, and really we replace mass with a rotational inertia. So following this same strategy here, we can actually rewrite Newton's second law. So we have Newton's second law says the sum of the forces acting on an object is equal to the object's mass times its acceleration. Replacing this with the linear quantities, we can rewrite Newton's second law for rotational motion. And it's not a force, if you remember back, it's not just a force that causes rotational motion, but it's a torque. And so instead of saying the sum of the forces, we can say the sum of the torques around any point. Around any point would be equal to instead of the mass, we are going to replace mass with the rotational inertia, and instead of the acceleration, we're going to replace it with the angular acceleration. So the sum of the torques is equal to the rotational inertia times the angular acceleration. So if you remember that torque is equal to the perpendicular force times the moment arm. And so then we can say that the perpendicular force times the moment arm or the lever arm is equal to the rotational inertia times the angular acceleration. This is really, and it's really the net torque. So this should be the sum of all of these perpendicular forces times their moment arm. So we have really, this is just Newton's second law for rotation. We talked about a second condition for equilibrium previously, when the net torque or the sum of the torques were equal to 0. This follows then that the rotational inertia times the angular acceleration would be equal to 0. And since the rotational inertia is not 0 unless all the mass is located at one point, we must have alpha equal to 0. So same definition that we had really previously with linear quantities. We have if the sum of the torques, so this is alpha is equal to 0. So if the sum of the torques are equal to 0, this means that our rotational acceleration is equal to 0, and we have rotational equilibrium. We also remember that, so just looking at this picture here, remember, the torque is the perpendicular force times the moment arm. So if I want to get this merry-go-round spinning as quickly as possible, so I want my largest angular acceleration, then I would apply my force to be perpendicular at the farthest distance away, and this is going to lead to the largest angular acceleration, which would then lead to the largest angular velocity as fast as possible. So there you have it. It's Newton's second law for rotational motion. The sum of the torques are equal to the rotational inertia times the angular acceleration.